Bismillahirrahmanirrahim. I am Dr. Syed Azhar. In this lecture, we will discuss basis and dimension of a vector space. In the definition, basis is basically a spanning set, which we have already studied in previous lecture number 8. If the vector in the spanning sets become independent, then such spanning set is known as a basis for a vector space. For example, in the previous lecture, we already discussed a collection consists of 1 0 0 vector, 0 1 0 vector, and 0 0 1 vector. That this set was a spanning set for R cube. Since the vectors of this spanning set are also independent, you can check it by using this equation: x1 u1 plus x2 u2 plus x3 u3 is equal to 0 vector. Also, you can take help from the previous lecture number 7, which was related to independent and dependent vector. Since the vectors in this collection are independent, and this collection spans the whole vector space, so this collection is a basis for R cube. Now, the definition is a set S of vectors is a basis of vector space V if it has the following two properties. Number first, the vectors in the collection S must be independent. Number two, S must span the whole vector space. Also, you can write its definition like this: if every vector of a vector space can be expressed uniquely in the linear combination of this set, basis set. So for the basis, you have to verify two properties. Number first, the collection must be independent. Number two, the collection must span the vector space. And we will solve some problems on this topic also. Now, what is the definition of a dimension? The number of vectors in a basis. The number of vectors in a basis is called dimension of a vector space. Now clearly look at this spanning set. Since this collection spans the whole vector space R cube and these vectors are also independent, so this collection is a basis for R cube. And what are the number of vectors in this collection? That is 1, 2 and 3. So the dimension of R cube is 3. Now these are the main points related to basis and dimension. Number first, a vector space is said to be finite dimension or n-dimensional if the number of vectors in its basis is n. Number two, the vector space consists of only a zero vector is defined to have dimension 0, means the dimension of this vector space will be 0. If a vector space does not have a finite basis, then such vector space is said to be of infinite dimension or to be infinite dimensional. These are the main points related to basis and dimension. Now we will discuss some theorems related to basis and dimension. It will help us to solve different problems. Now this theorem states that if we have a vector space of dimension n, then any n plus 1 or more vectors in V are linearly independent. As we have already discussed that a collection S consists of vectors 1 0 0, 0 1 0 and 0 0 1. We already discussed that this collection is a basis for R cube, and since the number of vectors in this basis is 3, so the dimension of R cube is 3. Because this collection spans the whole vector space R cube and these vectors are also independent. You can verify these vectors easily and can take help from the previous lecture number 7. If we incorporate another vector in this collection, then this collection will become 1 0 0 vector, 0 1 0 vector, 0 0 1 vector, and say we incorporated another vector a b c. Now this new remember, this new collection will remain a spanning set for R cube, but this collection will not be independent, and you can verify these vectors very easily. Since the number of vectors in this collection is 4, that is 3 plus 1, and the dimension of R cube is 3, so the number of vectors more than 3, that may be 3 plus 1, 3 plus 2, 3 plus 4, and so on. If the number of vectors in a collection is more than 3, then that collection will not be a basis for R cube. So we can generalize this result. If the number of vectors in a collection is greater than the dimension of a vector, then such collection cannot be a basis for a vector space. Number 2, if we have a collection, say S consists of n vectors, as the dimension of vector space V is n. If the collection consists of n vectors and this collection is independent, then the collection will be a basis for a vector space. The third part of this theorem is, if a collection has n number of vectors and this collection spans the vector space, then this collection will also be a basis for a vector space. The second and third part of this theorem tells us that if we have a collection consists of n number of vectors for a vector space with dimension n, then there is no need to check both the properties for a basis. We will check only one property. Either we will check the given collection is independent or the given collection is a spanning set. Now, in these two parts of this problem, we will use that theorem related to basis and dimension. Since in first part, the collection S consists of 4 vectors and the dimension of R4 is also 4, so we will check only its linearity. First of all, we will write these vectors in a matrix form. Say A is equal to 1, 1, 1, 1. This is our first vector. Our second vector is 0, 1, 1, 1. Third vector 0, 0, 1, 1. Fourth vector 0, 0, 0, 1. Now look at this matrix. This matrix is in proper echelon form, and we already discussed that row operation basically eliminate the dependent row, means the dependent vector, and we observed that there is no zero row, means each row is an independent row. So this shows that all these rows are independent rows, means all these vectors are independent. Since this collection S consists of 4 vectors and all these vectors are linearly independent, so there is no need to check whether this collection is a spanning set for for R4 or not. By using the previous theorem, this collection is a basis for R4. Since all the vectors are linearly independent and the number of vectors in the collection S is 4, so that is equal to the dimension of R4. Hence S is a basis. Since all the vectors, these vectors are linearly independent and the number of vectors in this collection is equal to the dimension of R4, so this collection S is a basis of R4. Now we move towards the second part. The second part is so easy because we know that the number of vectors in the collection must be equal to the dimension of a vector space. Now look at this collection. This collection consists of 1, 2, 3, 4 vectors, and the dimension of R cube is 3. So this one is basically not a basis because this collection may be a spanning set, but these vectors must be dependent vectors. So in second part, S is not a basis. Now we will discuss some more points related to this topic. This theorem tells us the relation between a subspace and a space. For example, W is a subspace of a vector space V. Then the dimension of W will be less than or equal to the dimension of a vector space V. If the dimension of both vector space and subspace both become same, then we will get W equals V. Means there will be no difference between the subspace and the vector space. Means both will be the same vector spaces. In this example, for example, we have a vector space R cube and W is its subspace. We know that the dimension of R cube is 3. Number first. Now, if the dimension of this subspace W is 0, then W will consist of only a 0 vector. Means origin, means a point. Number 2, if the dimension of the subspace is 1, then W will be a line passing through the origin in the XYZ plane. For example, we have this XYZ plane. In this case, if dimension is 0, then W will be consist of only this origin. And if the dimension of the subspace is 1, then W will be a straight line passing through the origin. This straight line may be this one, this straight line can be this one, this straight line can be this one. This may be any straight line passing through that origin. Number third, if the dimension of the subspace is 2, then W is a plane through the origin. Means in XY plane, say this one is our x-axis, this one is our y-axis, this one is our z-axis. Then this plane will be xz plane, this plane will be yz plane, and this plane will be xy plane. Now look at these planes. This xz plane is passing basically through this origin, and in case of dimension of W equals 2, then W is a plane through the origin, represents this plane or this one. Number 4, if the dimension of the subspace becomes 3, now look at the dimension of the vector space R cube, that is also 3. In this case, both the spaces W and V both will become same, means both will represent the XYZ plane completely. So this is the end of this lecture, basis and dimension. Hope so you will enjoy it. Feel free and ask questions in the comment section. I will reply inshallah. Thank you.